Section 4.6, working still with exponents and logs, And I go back to that log base b of x equals y, then b to the y power equals x. Able to jump from an exponential equation to a logarithmic equation, back and forth, back and forth. Log base b of x, that's not to the x power. I need to make my x down here a little bit closer to the word log. Log base b. So keeping that in mind, I'm taking a look at these first two problems because they're going to help me do certain things. And in this case, solve for a specific variable. Okay. And in the first one, I want to get the d alone. Second one, oh boy, I have an x up there as part of my exponent. I want to get the x alone. So let's take a look at these and see what we got going. I want this term by itself, s minus 23.5 equals 2 log of d. Well, there's no base down there, so we know that to be the common log. So all I did was subtract 23.5 from both sides. I'm now going to divide it by 2. S minus 23.5 over 2 equals log of d. Oh, this is going to be kind of ugly. 10 to the womp power equals d. 10 to the s minus 23.5 divided by 2 power equals d. Well, I subtracted 23.5, got this term alone, divided by 2, then converted the log to an exponential. Well, alrighty then. Let's take a look at number 2. This time it says solve for x, get the x alone. Well, I'm going to let this as 3e to the n x power, and I'm going to add t to both sides. Okay, hopefully you're picking up patterns as I'm doing these to help you learn how to solve some of these. I am going to now, let's see, divide by 3. That's not too bad. E to the n equals 4.2 plus t divided by 3. That exponent up in the air is a problem. I'd like to get it not up there. So what I'm going to do is take the log of both sides. What might be better than the log? What if I took the natural log? Yeah, let's just start with the log. So now I get n times x log e equals the log of 4.2 plus t over 3. As you can see, I can now get x alone. I'm going to divide by n and I'm going to divide by log e. X equals this whole guy, log of 4.2 plus t over 3 divided by n log e. I accomplished what I needed to do. Get the x alone. Solve for x. Again, I had that as an exponent. One way to bring it around, log of a side. Now, by the power rule, I can bring that exponent to the front. Oh, yeah. Yeah. Are there any questions? Well, I don't know. Yes, a question. Student interaction. Go ahead.
Are we going to get like this type of questions in the test?
Probably not that difficult.
Okay.
Something easy.
Yeah, it is really difficult.
And it's one of those, the more you do, again, the easier they become. So, all right. So, what do we have here? Well, let's read the question. Suppose that at 19 years old, you win $100,000 playing the lottery. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under continuous growth. Oh, we did the continuous before. Yes, we did the continuous before. We had this guy, PERT, and this was my amount. Okay, this is my initial. We did something along the lines of, this was my initial amount. So grandma gave me $8,000 to invest continuously at a rate of 6%, and say I wanted to end up with $20,000. How long would it take? Kind of deal. This is my initial amount. Sometimes you'll see this written as P sub 0, e to the RT equals P, right? But I'm given $8,000 at 6%. It's compounded continuously. That's where this formula came from. It's compounded continuously.
What does that continuously mean? Is it yearly?
Well, remember we talked about yearly, and then we said, okay, that was well, and then we said monthly. And when we did the monthly, we did that initial amount and then 1 plus R over N to the NT.
Yes.
So I took whatever my rate was, and I would be dividing it by 12. Mm-hmm. But if it was for 3 years, I multiplied it by 12 to get to 36. Mm-hmm. So if it was monthly, I'd have 1 plus R over 12, and then 12 times the number of years, so that it's compounded. But then I said, well, what if it was minutely? Oh boy. Well, maybe let's go with daily first. Daily was 1 plus whatever that was, 365. 365 times T. And you notice this keeps getting larger and larger and larger. In fact, if I went, well, they're offering you daily, and the reason this is good is because you're getting interest on interest. I'm not going to go daily. I'm going to one-up you, and I'm going to go hourly. So that would be 365 times 24. So this number keeps getting bigger.
Yeah.
And then if I
smaller,
this right here would now be
365
times 24 hours.
Yeah.
And then minutely would be that times 60. And I said, well, I'm going to calculate it every second. So what happens is when this n gets larger and larger and larger, this equation actually, and we're not going to get into the algebra of it, turns into P times E raised to the RT. So this guy becomes this when we want continuously. That means faster than every second. Sounds bizarre, but that's what it is.
Okay.
Yeah. So I want to go continuously. All right. And that's where this comes in. This is kind of like the PERT. P E to the RT. The P here, Y sub 0 is the initial value. E to the K, T kind of deal. Okay. All right. Suppose a 19-year-old wins $100,000 playing the lottery. That's going to be that first P, right? Because that's how much I want to. That's how much money I have. I'm going to read the whole question first. He'd like to have $1 million. I'm pretty sure that's going to be the A. When he retires at age 67. Determine the average rate of return needed under continuous compounding. All right, so I know my equation. A equals P e to the RT. This P was my initial amount. That equals $100,000. He'd like to have A, which is $1 million. So I have P, I have A, E stays. He'd like to know what rate, so I don't know R, but when he retires at age 67, so this would be for how many years? Well,
57 minus 19.
yep. So T would equal
48.
48. Okay. Compounded continuously. Initial amount, what I'd like to end up with, or final amount. So let's see, $1 million equals 100,000 times E raised to the R times 48. I would like to now solve for R. What rate would I need if I took this $100,000 away? Well, this is sort of like we were doing at the top of the page. I'm going to divide 1 million by 100,000. That's not so bad. That becomes 10. Oh, this is one like I practice. I need to get the logs and bring it around. But instead of logs, I'm going to do natural log. And I'll tell you why. If I do log of x is like log base 10 of x. If I do natural log, the natural log of E, remember that was the same as log base E of E, and that's 1. That's one of those, if we had another day to practice more and more stuff with logs, that would be great. So when I have a base that's E, I'm going to take the natural log of both sides. Natural log of 10 equals natural log of E and 48R. Swing your partner. Natural log of 10 equals 48R times natural log of E, but I know that is now 1. Oh, natural log of 10 divided by 48 equals R. Calculator, oh, that's my phone. I need natural log of 10. I'm excited. Natural log of 10 divided by 48. He needs a rate of 0.049797. So he needs 4.97%. That even makes sense. Everything sounds good there. My hopes are you were able to follow along. My hopes round 2 are if you went back over and looked at this, you would be able to figure it all out. 100,000, that's my initial amount. I'd like to have 1 million. That's where I would end up when I'm doing all this compounded continuously. We don't know what rate, that's what he's trying to find out, but he wants to let the money sit for 48 years.
I think it is not 4.79%.
I don't know, did I do it wrong? I may have looked at it wrong. You're telling me this is 0.0479?
Yes.
Thank you. 4.79%. Thank you.
So we should round up. Still, it's gonna be 4.48%.
I would leave it as this.
Oh,
Either way.
okay.
Yeah. The more accurate, the better.
Mm-hmm.
Yeah. Awesome. I like that problem.
Oh, this one is interesting.
Make sure you understand this for Thursday. I'm going to give you another one of these. Okay. Moving right along to 4.6. Two more. We're only going to do 4 and 5, and then we're going to stop. I think we'll have okay, anyhow. According to a study published in 2012, again, this would be awesome in a classroom because I would have you sitting together in groups of 3 or 4 and let you work on this to see if you can get it started. According to a study published in 2012, Burmese pythons are becoming new top predator in Florida. Okay. Not many animals in the Everglades can stand against a python that can grow 23 feet long and weigh over 200 pounds. All right. That's a nice, interesting paragraph, but I think that's really not much information for us. 20 pythons were recorded as captured or killed in 1995. By 2019, that number had increased to 378. Right of function to represent the number of pythons. Okay. So here it is. That P sub 0, that's my initial value. So that's going to be how many pythons?
20.
20. At the end of that time period, there were 378 pythons. This is going to be E raised to represent the number of pythons captured in or killed in T years. So let's see, what do I know? I don't know the rate. Again, I don't know the rate, but I know what the
Time is
time is. And time is what?
2009 minus 1995.
Times, you have a
14
number?
years.
14 years. Good. Excellent. Excellent. So it says write a function to represent the number. Okay, we want to write a function in terms of t. Well, let's see if we can calculate r. Okay, we have enough information to calculate r, but then we're gonna get an equation so the user can put in the number of years instead of 14. So this is like my initial equation. Oh, divide by 20. Looks like I get 18.9 equals e to the 14r. I want to be able to solve for r. What is r? Natural log, because I know the natural log of it. And then I'm going to bring the 14r around, right, by my power rule. This just becomes 1. So I have the natural log of 18.9 over 14 equals r. This becomes 1. Divide by 14. Looks like I get an R of 0.21. So what we're saying is, I don't know how many there'll be, but this is in terms of time, equals, and this guy is going to be 20 E, because this is all since 1995, 0.21 T. So if I said, hey, given the year whatever, I can now plug that in for T, and we would see how many stinking pythons there are. Okay, so using the model from up above, our model is P sub T equals 20 e to the 0.21 t power. This is now for 2017. So it looks like that's going to be about 22 years. Yeah, this was after 14 years. After 14 years, they were up to 378 snakes. Now, after 21 years, we're going to see how many snakes there are. So it's going to be, oh boy, 20 e to the 0.21 times 22 years. I don't like spiders and snakes. My equation was 0.21 times 22. I got that. I now want E, found E raised to the 4.62 power. And now I'm going to take that times 20. And it looks like, oh, 2,030 snakes in year 2017. My initial data helped me create an equation. I'm now using that equation. And ooh, that was killed or captured, right? Killed or captured. Ugh. If the ratio of pythons living in the wild to the pythons killed or captured is approximately 100 to 1, how many pythons were in there in 2012? 2012, let's see, T is going to equal 17. So 17 goes into my equation. 20 times E raised to the 0.21 times 17 power. Now I can do that on my calculator. Okay, I'm going to do 0.21 times 17. I'm going to do E raised to the 3.57 power. I'm going to multiply by 20. So that means there were 710 killed or captured in 2012. But if it's 100 to 1 ratio, the 71000, 71,000 snakes alive in 2012. I have a trip to Florida coming up. I am not going to the Everglades. I don't know about you. No, not going to happen. Dang, if I use this equation, I don't even want to know what it would be for the year 2022, where we are now. There was 2,000 in 2017 times 100. That means there was 20,000 living in 2017. I don't know. No. Let's look at one more. One more. Again, this compounded continuously is great. A sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. 2% is going to be my rate. Rate equals 0.02. I'm pretty sure that's going to become important. All right. Something along those lines. No, cross that out. I don't want to do that. Don't write that down yet. Carbon 14. Use the model for radiocarbon dating, where Q sub 0 is the original quantity of carbon 14. Okay, this is gonna be a little odd. So a sample collected from, and this is hard. This one is legitimately hard, but you may come across this in a course somewhere along the line. Okay, so let's see. A sample collected from cave paintings of an archaeological site in France showed that only 2% of the carbon 14 still remains. How old is the sample? Well, we're given this equation, Q of T equals da 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 with the T. And the T is what we'd like to calculate. Now, this guy right here, the amount we want to end up with and the amount we start with, we look back up here and say only 2% remains. So that means the 2%, and this is one of those where would have been really difficult to find. If I divided Q of T by Q of 0, that would give me this 0.02. And unless you're really into carbon dating, so for you to set this up would have been very difficult. But what you end up with is 0.02 equals E to the negative 0.1231221 T power. Now, this is where math being a partner discipline comes into play. You're not an archaeologist. You're not, getting this whole carbon dating and how this amount divided by that amount gives me the 2% remaining. But now as a mathematician, you need to be able to come up with the answer to this. So we want to know how old this sample is. And again, where did that negative 0 down at? We don't know any of that. We just know from a math perspective, we can jump in here and solve this. Natural log of 0.02, again, because of the E, I can bring that exponent around, negative 0.000121 T times the natural log of E. Remember the power rule. And I also know the natural log of E is gone. So T is going to be the natural log of 0.02 divided by negative 0.000121. We're going to find out how old this thing is. Natural log of 0.02, and I hit enter, and I'm going to divide that answer by 0.123121, and I get something that, oh, I forgot to make that a negative because it was a negative, which turns this answer into a positive, 32,330 years old. And again, for you to understand the equation, looks familiar. I can work with exponents, but to get to this, there's a whole nother discipline of archaeology, whatever that is, that would help you set this up, which is what I did. But now you should be able to go to town.